next speaker is Sasha Brenner. He will talk us about near-horizon symmetries and charges of magnetized black holes. We can start.
Okay, thank you very much, Marcela. And I would like to thank the organizers for having me and encouraging students to participate and share work. I have to confess that this is my first talk ever, so I'm very excited, but also indeed a little scared, I guess. So I will speak to you about something we've been working on in collaboration with Lucho Montecchio here and Gaston Chiribet, with Gaston as the supervisor for my licenciatura thesis, the near horizon symmetries and charges of magnetized black holes. But first, let me introduce a little motivation that Gaston also mentioned in his presentation, which belongs to the same line of work. He talked about extremal black holes. So in 2000, very briefly, 2016, Hawking, Berry, and Strömger proposed that asymptotic conserved charges, which stem from an infinite set of diffeomorphisms on the black hole event horizon, might encode information that could then be radiated away without any theoretical loss. Of course, this is something that, as Gaston mentioned, is not the central point of the work, but it's the original motivation for this. Gaston and other colleagues pursued this line of work, and they proposed a physically relevant boundary condition, which they showed were preserved under an infinite dimensional symmetry group as predicted. And it's not exactly BMS, but it contained BMS. So they also calculated the associated nether charges for various black hole solutions and even more general known surfaces like apparent and cosmological horizons. And one of those charges in particular turned out to be Waltz entropy. So with Lucho and Gaston, we incorporated backgrounds of strong magnetic fields to the black holes, which are particularly relevant in certain astrophysical scenarios, such as active galactic nuclei and highly magnetized objects. And we actually also worked with other metrics, like the C metric, but this talk will focus exclusively on magnetized black holes. Okay, so I'm gonna very briefly review what Gaston talked about a few talks ago, but not with much detail since time is scarce, and I definitely cannot explain this any better than he already did. So these here are the boundary conditions I mentioned. We can always put the black hole metric in a set of advanced coordinates, v, rho, and the angular momentum coordinates, the angular coordinates z1 and z2, such that when rho is very close to 0, that is close to the horizon, which is at rho equals 0, the metric can be put in this form right here. So the ellipsis indicates the subleading terms of order rho squared and or bigger. So a couple of remarks. Kappa here is the surface gravity, as a matter of fact, and we assume it to be constant across the horizon. So we assume that we are in quasi-thermal equilibrium. And the functions NA that appear here and omega AB, they are functions of the angular coordinates only. So in principle, they could be functions of the advanced time V, but we're going to assume that they're not. And this is to ensure the integrability of the charges. Okay, now, given these boundary conditions, there is an infinite set of asymptotic killing vectors that generate diffeomorphisms which preserve the form of the boundary conditions. So note that the functions defined in the previous slide, they need not remain the same after the transformation is applied. What must remain intact is the form of the asymptotic metric. So its structure. And that is why it can be shown that there is, in fact, an infinite number of such killing vectors corresponding to the infinite set of functions, YA here and T. So these give rise to an infinite dimensional algebra that just to mention it, 2 copies of beta soda generated by the YA, the super rotations they are called, and 2 current algebras generated by T and another function which is not here, and I will show you on the next slide, that they are the super translation. And these functions can be further decomposed into normal modes, and commutation relations can be obtained. And in this way is that one shows what basically what I just said. So the conserved charges, right? So they can be calculated making a couple of assumptions that I already mentioned, and choosing a convenient gauge, which is called the conformal gauge here. And one gets the expression that is shown right here on the screen. As I mentioned, one of those charges, namely setting t equals 1 and ya equals 0, we get is the Waltz entropy, right? So this is Waltz entropy. But we will be working with magnetic fields and charged black holes, so we want to also regard the electromagnetic field and its own asymptotic behavior. So now, in addition to the diffeomorphisms of the metric, we will have a set of asymptotic gauge transformations for a mu. Associated to them, we have a new function, u, that appears here, that is a function of the angular coordinates, and it takes part in the final expression right here for the charges. So, okay, so this is the expression of the charges that we will use herein. So, we want to apply this to magnetized black holes. So to do that, we use solutions obtained through a prescription devised by Ernst that I will talk about in a minute. But the background on which the black holes are embedded, though, is the Melvin magnetic universe. It is called, it is shown here. It can be thought to represent a bundle of magnetic field lines attracted to each other through their own gravitational pull, all along the z direction and concentrated around rho equals 0. So this metric has no sources, okay? The field is like stable on its own. It doesn't need sources. It's not produced by any sources. And it is worth noting that this metric is not asymptotically flat. And in this sense, it is unphysical. But it can work, though, as a good approximation of a region of space with strong magnetic field for a small enough value of the coordinate rho. Note also that the metric is, in a sense, like it. I mean, if you don't take into account this term, it would be like conformal to Minkowski. It's not, of course, but the reason is that these 3 terms are multiplied by lambda squared, and the phi term is multiplied by lambda to the power of -2. I just mentioned this in order to make a comparison very soon. Okay, so in 1976, Ernst presented a prescription to produce black hole metrics that bear resemblance to the Melvin magnetic universe. So given the line element of, for example, the Schwarzschild metric, it could be any stationary axisymmetric line element, the Ernst procedure spits out a new line element and an electromagnetic field that is fully coupled. In this case, in the case of the Schwarzschild metric, we get this line element. So as you can see, this f of r that appears here is exactly the same factor that appears in the Schwarzschild metric. In fact, this would be, again, in this sense, conformal to Schwarzschild if it wasn't for the fact that the factor lambda squared is multiplying these 3 terms, but dividing here in the d phi squared term, just as it happened before with Melvin with respect to Minkowski, right? So in the limit of r approaching infinity, we obtain the Melvin universe, since the factor lambda is exactly the same. If you don't remember, it's exactly the same as it was before. And the 3 Schwarzschild terms here inside the bracket look like Minkowski at large r. So, okay. So this is Schwarzschild embedded in a magnetic field, basically. If we now feed these mechanisms with the charged black hole metric, that is Reissner-Nordström, we shall obtain a charged magnetized black hole. So the factor F of R here is, again, the same as that which appears in the ordinary Reissner-Nordström metric. But in this case, though, the line element is not even almost in this sense conformal to Rn, because we get a new cross term here of d phi dt that didn't exist in ordinary Reissner-Nordström. That is, there is some kind of rotation, right? So this makes the charged Ernst metric interesting to study since, for example, the magnetized Kerr or Kerr-Newman metrics, they are way more complicated, but this metric already features rotation, which means that it can have some superrotation charge.
5 more minutes.
Thank you. This metric possesses many interesting properties which have been studied in the past, for example, by Gibbons in 2013, and in particular, this solution almost always exhibits an ergo region that extends to infinity, which makes it clearly not asymptotically Melvin, because Melvin, the Melvin universe, does not have an ergo region at infinity. This does almost always. Finally, note that the angular velocity here, omega, the angular velocity is dependent on r as well as theta, and it can be defined up to a constant. And this comes from gauge freedom, and we choose it so that that constant so that omega is 0 at the horizon. So at r equals r plus, we get omega equals 0. Good. So here you can see the expression for the corresponding electromagnetic field calculated by the same mechanism, the Ernst mechanism that I talked to you about. And this, of course, reduces to the charged sphere when the parameter B is equal to 0, because then we would also only have a Reissner-Nordström, and to the Melvin field when M equals to 0, because then we would only have a magnetic field. Okay, so in the next 2 or 3 slides, I will very, very briefly tell you about a couple of things that we had to arrange before calculating the charges themselves. And first, let me talk to you about the conical singularity that's present at the poles. That is, there is an angular deficit at the poles. But the good thing is that it is exactly the same at both poles, at theta equals 0 and theta equals pi, and that is because of the symmetry of the metric with respect to the xy plane. So we can fix both singularities just by fixing either one of them. And it suffices to extend the domain of phi to this value over here. That is, it increases with the magnetic field. Okay, second. This was a crucial and quite hairy part of our work. It was finding the change of coordinates necessary to impose asymptotic boundary conditions, the asymptotic boundary conditions we talked about a few minutes ago, to the line element of the charged Ernst metric. So as you can see, we defined the advanced time here with reference to the tortoise coordinate, that is this integral over here as is typically defined, and the rho coordinate is defined in such a way to take the value 0 at the horizon, r equals r plus, because of the limits of integration, and also this lambda squared, absolute value of lambda squared in the integrand is there to fix the required gauge. Note as well that the new phi is just the old phi at the horizon, because at r equals r plus, this integral is 0. So the coordinate doesn't mix at the horizon with the other angular coordinate, and that was quite important. Next, finally, the gauge fixing condition, which is well, nothing, just this gauge fixing condition that we needed, that a rho equals 0 for the validity of the simple expression of the charges that was shown previously. Great. So finally, recalling the general expression for the charges, we can calculate the few simplest of them to make some interpretation. So for instance, setting t equals 1 here and all the other functions u and y to 0, so this is only t equals 1 and the rest 0, we get, as stated before, the Waltz entropy of the charged magnetized black hole. So the coupling of charge with the magnetic field, because this factor lambda 0 squared is over here, and it depends on the coupling only of the magnetic field and the charge. The coupling of the charge gives the black hole entropy, since it makes it grow in size. And the physical electric charge is a little smaller than the original charge parameter Q, and this result was already obtained in the work I mentioned, for example, by Gibbons, and it is in coincidence with what's shown here. Well, of course, the theta charge angular momentum is 0 because of the symmetries of the metric, but as predicted, there is azimuthal angular momentum. So it is worth noting that this does not depend on the mass of the black hole, but only its original electric charge, Q, the parameter, right, of Reissner-Nordström. So one could say is not all that surprising that an angular momentum is generated upon the turning on of the magnetic field, because the classical electromagnetic field itself has an angular momentum, and so the coupling with Einstein's equations likely produce some sort of dragging, even though I'm not 100% sure yet about the actual physical interpretation of the origin of this rotation, but I'm on it, we're on it. And so, well, up next, the Meissner effect. We're studying the Meissner-like effect that should be present in this metric, trying to understand it better. But well, thank you very much for your attention. That's it.
Okay, thank you for your interesting talk, Sasha. I don't know if there are any questions for Sasha. I don't know. Well, I have a question, Sasha.
Yes.
Can you listen? Yes. About the charges, well, you showed any charges that are already integrated, but I imagine that you use a method where they are not integrated. And what you got is the variation of a charge.
You mean this expression, right?
Yes, exactly. So I would like to know a little bit more, because at the end, those parameters that appear there, some of them are physical choices that I assume you impose on the asymptotic Killing vectors, on the parameters of the asymptotic Killing vectors.
Yes, so actually, this was, I mean, Gaston and Laura Donay and Gonzalez, they worked on this in the previous works. They used a method called I don't remember exactly but it's like a very complicated. I honestly don't understand it. I mean, I didn't even try to, because mathematically it was like way over me. So, but I don't know. Maybe if I don't know if Gaston is here, maybe he can tell you something about that.
Yes, I seen a comment of Marcela is about integration in the phase space, no, the integral. Yes, her comment is good, because typically these charges, the method we use gets the functional variation of the charges, and it's not necessarily the case that this can be integrated. But always you have the isolated horizon, which are some conditions, namely the induced metric on the horizon doesn't change, or the surface gravity is constant. Then the charges are integrable. We studied this with Pino and Gonzalez and Donet. And in the case Sasha is considering, is her isolated horizon. So then the charges are integrable, and that's why he managed to produce an already integrated expression.
Okay, thank you. I don't know if there are more questions. Well, I have one extra question, but it's not a question. Maybe you haven't talked about it, but I don't know if you have. I mean, one motivation of this magnetized solution is somehow related. If you're aware of the Blanford-Synergic process, if you are have something in mind
a little
about
bit.
it.
Yes, I studied them a little bit. Yes, that's very interesting. Yes, yes. Actually, there is work by, I think he's called Sijak, that actually uses some of these methods to study specifically those kind of, I mean, the implications of this to those kinds of processes. And actually, I'm getting into that, like I've been getting into that in the past week or 2 weeks. So you were going to ask something about that. Maybe I don't know if I can say anything, but.
No, I was just wondering if you have some motivation related to that aspect.
Yes, of course. Yes.
Nice. Okay.
Yes.
If there aren't more questions, well, let's thank Sasha again. Very good talk.